I want to see how this is going to come out. So I'm interested. Okay, so I think we're fully discharged. We're just now waiting on the LabQuest to boot up. Once it boots up, we'll be able to take some data here. So I want to try and actually get some decent data. I really don't know why the spike occurred yesterday, and I'm kind of interested in that too. So we don't need yesterday's. We're going to do this a couple different ways. I think the first way we're going to do it is qualitative. I want to make sure I have all of my things connected in the right direction, and I'm not convinced that I do. So the first thing I want to do is apply the potential, and we can see that the red bar is the current that's passing through the circuit. The blue bar is going to be the, got to figure out which is which. Well, we'll know when we start it, but the blue one I think is the voltage across the capacitor, and the green one is the voltage across the resistor. All right, now we'll know if we're right because the moment we connect it, the resistor should have all the voltage and the capacitors have nothing, and then they should swap. So you guys at home, can you see all that okay? I have to take their words on it, but I don't hear them. So
yes.
Good, because your boxes are really small from where I'm standing. Well, I think we saw what we thought we'd get. Oh, that red wire, it's just going to be there. So green box started big, is getting small. Blue box started small, is getting big. It's all good news, right? Current's positive. I like that. So it looks like everything's set up in the direction that I want it to be. I'm going to wait for it to get fully charged. We know we're going to be there when we get the same voltage across the capacitors we expect across the battery. It's a 6-volt battery. So how long was that? 30 seconds? I mean, it's slowing down clearly, but how long till we reach a steady state condition? Now, we've used voltmeters. Do we ever actually get a steady state condition, or they always seem to be fluctuating at the end? And I think we're going to see something similar. I mean, we're close, but, you know, are we going to have fluctuations at the end? A little bit. Seems like it's pretty steady, though, even now. We're talking 3 decimal places, so we're down to the thousandths place. You guys can. I guess I'm standing in the way of you seeing it, huh? Sorry. So let's watch the discharge. When I connect this together, we expect the voltage on the capacitor to stay at its max and descend. The voltage on the resistor, though, when we look at it, the voltage on the resistor also has to descend. So what we're expecting is that immediately when we connect this, we're going to see a voltage on the capacitor and an equivalent voltage on the resistor. And they're both going to drop at the same time at the same rate. The current's going to start at a maximum and it's going to drop at the same rate. They're all three the same equation. The only difference is that one voltage is the inverse of the other. So let's see how that goes. See, that worked out, didn't it? Give that a few seconds. But I am interested to see how long it takes to get to 0. I'm not sure it'll ever get to 0, but looks like it's about the same. So how long do you think this is taking? About 40 seconds? Is that still a good time? Or should we go longer, maybe a full minute? How long till the bell rings? All right, so we can do this a couple times. I'm going to connect this so that we can actually get the real data as it's collected. So I'm interested in how this is going to go. I think that's as low as it's going to get. Feels pretty discharged to me. Won't you guys think the same way? Or do you want to wait a little longer? I mean, I don't really see it dropping very much after this. And I don't think we're going to get all the charge out. I don't think we're going to get it all down because I think we're going to start reaching the limits of the ability of the device to measure voltage. Remember, this is still an active device. It's having to measure current, measure voltage. It's actively adding to the system in order to measure those things. This is why a voltmeter takes a battery, because it actually applies a voltage to things and it draws some current and creates some current to try and make these measurements. So we're going to go with, go for a minute, 60 seconds. And I think 10 samples per second is still pretty good, don't you? So, all right, so we're ready to go. I'm gonna get partially set up. And I still say we want to get this started first and then connect it so we can see the initial change. So start taking data and connect it. This is a great set of data. I'm very excited. I like it when things work. This clearly seems to be working. Of course, I see a weird hiccup in the current. Do you guys see it too? Somewhere around 30 seconds. I think I know what it is. And I want to do the experiment a second time, but let's keep in our mind that there's a weird hiccup at 30 seconds. I want to see if this hiccup occurred. I want to see if we can detect what it is. I think I know what it is. So that's one set of data, but I mean, you guys see that at 30 seconds. That's something's wrong there about the current. You guys see it over at home too? So I'm going to save this because I think this is a great set of data. And maybe let's save. This will be the first run. This will be our charging data. So we're going to try it again. But this time we're going to do the discharge. So I want to discard this run. I already saved it. Still got that little spike there right at the very beginning, but I'm not sure what to attribute that to. I want to see if we see the same hiccup at 30 seconds. Clearly, we have the same hiccup right at 30 seconds. And I'm 100% confident I know what it is. So for you guys who want to see what it is, we'll hit the lights. And you guys at home and you guys here in classroom, if you have a stopwatch, so you know when 30 seconds is, I mean, I can tell you when 30 seconds is if you want, but I think I know exactly what it is. So I'd say that's another pretty good set of data, but the hiccup in the current is exactly the same point. And I'm happy to see it because it's good to know that, you know, this is going to be discharging. So discharging. Run 1. All right, so let's start again. And this time we're going to charge again, but instead of you guys watching the graph, I'm going to have you watch. And I'll get it started again. Let me get this plugged in. And Okay, we're at 15 seconds.
Teachers, pardon this interruption. The winner of the teacher gift card raffle for
25
this
seconds.
hour is Miss Keys.
30 seconds. You guys see what it is? It's right when the light bulb goes out. Why do you think we're getting this fluctuation right when the light bulb goes out? Go ahead.
Maybe the resistance changes when the light bulb's turned off.
So if you guys didn't hear that, Alex is saying that maybe the resistance changed when the light bulb turned off. I think that's exactly what it is. First, you'll notice the voltage didn't change at all, but the current did. If the current had a quick change like it did right then, that would be we're seeing a change in the current, but that has to be attributed to a sudden change in resistance for the same voltage. And in fact, if we look at the way that changes, we can tell whether the resistance increased or decreased by this change. I think it's because the bulb is colder. At the moment the bulb goes out, it gets instantly colder at that minute because it's no longer radiating as much heat as it was before. And suddenly it changes the resistance. I did not expect to see it so instantaneous with this set of bulbs. Last year's bulbs didn't do this. So I find it interesting, but I also think it's great that we have this. So let me save this one. This is run number 2. Charging. Run 2. And we'll do one more discharge, but I think that we've got some nice data for this. I want you guys to do this lab. So I know that I'm saving all this data and I'll have a good solid set for us to use. But I think one day next week, we should all set this lab up. So you guys at home, you don't have the 1 farad capacitors in your box, but I would be willing to send them out. They're expensive, but I'd be willing to send them out so you guys have them. What you don't have, though, is a lab quest at home. I wonder if I can send those home. Oh, I started to experiment. Oops, I didn't want to do that. Aww. Well, I know that signals happiness for you guys, but I'm still going to discharge this because I don't want to leave. Oh, wait, we're going to leave it charged all weekend. All right. We're going to leave it charged all weekend, so we're not going to get a discharge run. We're going to let it just sit there. So you guys at home have a fantastic weekend, except I will see almost all of you in a couple of hours. So have a great day. Talk to you all later.